Hello and welcome to Alkenes 7. So this takes a little bit of a kind of swerve away from electrophilic addition. We will come back to that a little, but it's really just kind of picking up a little odd and end in terms of something called hydrogenation, and then mainly talking about formation of what we call addition polymers. All right, let's get cracking. We've got some starter questions as usual. So usual kind of format, pause the video and have a go at answering these on a whiteboard or a scrap of paper, and then we'll have a look at the solutions. So you should have paused and you should have some answers in front of you, right? We've got a classify these carbocations question and then another question about the general formula for alkenes. So here we are. We've got secondary, primary, tertiary, and secondary. That's what the symbols mean, just in case it wasn't clear. The 2 degrees kind of sign, that's secondary, and so on, right? The only kind of trick here really is the bottom right one, which is still a secondary carbocation. It's different to the first secondary carbocation, but the trick here is that the molecule's been bent in a particular way in order to make it look like it might be tertiary, but it's not. It still contains a carbon which is bonded to another 2 carbon atoms, right? So there we go. All right. Next question was about buta-1,3-diene. So the easiest way to kind of look at this is to draw it probably. You could then convert it to a molecular formula. So because this alkene is what we call a diene, which basically means it's got 2 double bonds, right? That reduces the number of hydrogen atoms that it can have. So because it's got these 2 carbon-carbon double bonds, it's got fewer hydrogen atoms than but1ene or but2ene would. So it can't follow the general formula for alkenes, which is CnH2n. If you wanted to make a general formula for dienes, I guess you'd call it CnH2n minus 2, because you've got to take away an additional 2 hydrogen atoms thanks to that second double bond. You didn't have to come up with this. It's really just kind of for reference. Right then, let's crack on with something new. So this is kind of a very minor part of the alkenes topic, but another reaction that you can do with alkenes, as well as all the addition and electrophilic addition reactions that we've looked at, is another type of addition reaction, which is called hydrogenation. So basically the idea here is you can turn alkenes back into alkanes, all right? And this is a fairly sort of simplistic view of it. Let's say if we take ethene, we can add a hydrogen molecule across the double bond, right? And you can turn it into ethane, right? So this is still an addition reaction. It doesn't occur via electrophilic addition. It's a different mechanism using a form of catalysis called heterogeneous catalysis, which you learn about when you're doing sort of catalysis topic, probably in year 13. But it is still an addition reaction. So we're not going to look at it in any sort of depth in terms of how it works right now. Okay. The only thing I'm going to point out is that you would use a nickel catalyst, right? There are probably others, but that's the most common one we see quoted. And then I suppose if you gave a temperature for this, I've seen it quoted from anywhere between 60 to 100 degrees. Basically, they elevate the temperature a little bit, okay? 60 degrees is the standard temperature that's quoted for GCSE, but as usual, it tends to be a bit of a guessing game for certain temperatures, right? Chances are you won't be asked anyway. But hydrogen gas in the presence of nickel, right, a solid nickel catalyst, that will make this reaction happen. So the next thing to sort of point out is that this reaction is not very useful, right? There isn't really any value in turning ethene into ethane, because ethane, while it can be burnt as a fuel, right, you can't really do anything else with it. And there are loads of alkanes we can get by fractional distillation anyway that can be burnt as fuels. Alkenes are probably more, useful or valuable than alkanes are, simply because you can do something else with them, which is turn them into polymers, right? And we're going to look at that soon. So would you do this? If that's the question, the answer is probably no. Having said that, there is a reason why hydrogenation of double bonds in general is kind of useful, right? And that has to do with hydrogenation of vegetable oils, okay? So I'm not going to go into massive depth here, but basically vegetable oils contain very long hydrocarbon chains, right? There's more to the structure than that, but let's just assume that it looks something like that for now. Like there's actually a kind of bit in the middle and then another hydrocarbon chain, but don't worry about that, right? But they contain very long hydrocarbon chains, and very frequently they contain at least one double bond. If not, sometimes they have 2 or 3, right? And we call those unsaturated oils. And that's a term that if you ever read anything like about nutritional science, food science, you'll be familiar with. And the science surrounding whether unsaturated fats and saturated fats are bad or good for you, and which is worse, and then you include the geometry, the idea of trans fats. There are all these sorts of kind of arguments basically, and there isn't a total consensus about all of those things, right? Anyway, what I'm trying to say is there's a bit of an industrial context here. Basically, vegetable oils are liquids, right? And they are liquids because they contain double bonds, usually double bonds in the E configuration, right? That's not normally how we describe them, but you'd know it as the Entgegen form, right? And that gives them physical properties which raise their, which lower their melting point, and make them more likely to be liquids at room temperatures. From a sort of, food science point of view, one of the things that became very popular, I think, in the 70s was to take vegetable oils and harden them, right? And they do that by hydrogenation in the presence of a nickel catalyst. And the purpose of that is if you get rid of the double bonds, right, then you make more saturated fats, right? And that causes the vegetable oils to become solids. And those solids, from a kind of formulation or product point of view, we call them margarines, right? So you might not be aware, but butter is kind of an animal product, right, where there is a higher proportion of saturated fats naturally. Margarines are very much an artificial product where an oil has been taken and it's basically had a load of hydrogen added to it to make it into a spreadable solid. So essentially, I mean, I'm simplifying a little bit, but essentially margarine is solid vegetable oil, right? Or at least it's a vegetable oil converted into a more solid form. That's the only reason we might want to know about this, right? So that's kind of useful from an industrial, food science perspective. But like I said, with short alkenes, you probably would never bother doing this reaction, even though it's easiest to view them. The easiest thing to do for me is always to draw ethene and look at it. Okay, so let's move on from hydrogenation, okay? I mentioned earlier that the most common and valuable use for alkenes is to make what we call polymers, right? Generally speaking, the way that we do this is through something called an addition polymerization, which is a type of addition reaction. In this case, you're not actually adding anything across the double bond. What you do is you make a lot of these molecules, which we call monomers, react with each other. So it's basically the same thing reacting with itself over and over again to make a really long chain that we call a polymer. This is important because it's the basic, format for how we make many synthetic plastics, right? And plastics have obviously got a bad reputation at the moment because of the kind of solid waste problem that they cause. And potential ocean pollution, all that sort of stuff. But actually, you've got to face facts that plastics are very, very useful materials, right? All of the electronic equipment I'm using right now pretty much all of it has a plastic housing, right? A plastic casing. It's used in wiring. There's tons and tons of uses for plastics, right? And so addition polymerization from a, again, a chemical engineering point of view is a really, really important process, and we have to learn a bit about it. All right. It's actually really, really complicated, but the sort of easiest way to think of it is, again, high temperature and a catalyst, and we don't need to name the catalyst in this case. Let's have a look at how polymerization kind of works in terms of looking at structures. So there are 3 things we would usually look at when we're thinking about an addition polymerization. We would look at the structure of a monomer, we would look at the structure of a polymer, and we'd also sometimes look at something called the repeating unit, or the repeat unit is sometimes called. So here's the idea. If you have n molecules of ethene, n represents a very large number. For example, let's say it's 100,000 or a million, right? So that's the number of molecules of ethene you have. If you put the ethene in the correct chemical environment using the correct kind of catalyst, then it will undergo a reaction to form a polymer. In that process, one of the most crucial things we have to realize is that the double bond will be gone, right? And what happens in this case is not that we add, for example, you know, hydrogen or hydrogen and bromine or hydrogen and chlorine or whatever. We don't add stuff like that to those two carbons. Instead, you've got to imagine they're forming bonds outwards, right? And the thing that they're forming bonds to are other molecules of ethene, okay? So you can imagine like that double bond, the electrons within it are kind of used to form bonds to the left and to the right, okay, with adjacent monomers of ethene. The rest of the molecule remains exactly the same. And that's an important thing to realize when we're drawing polymer diagrams. These 4 hydrogens are the same 4 that were present in ethene to begin with. So it's only the bond on the left and the right that are new, okay? To show that this is a polymer diagram, we turn those into what we call trailing bonds by putting some brackets. So just to be clear about what this means, the brackets essentially tell us the structure doesn't finish here. There's a load of stuff on the other side of this bracket, but we're not going to draw it because actually it's the same thing over and over again. Basically, you wouldn't ever draw this, but just to explain, there's another carbon atom here from a different ethene monomer. There's another carbon atom here from yet another different ethene monomer, right? And then that just carries on and carries on. So because the structure is just repetitive and doesn't kind of change, right? We don't bother including all of the carbon atoms. It would be a pointless diagram. We have a kind of special abbreviated way of showing it. The only other thing we have to add to show that this is a polymer diagram is we put the little n down to the bottom right of where those brackets are. And again, the implication here is if you had 100,000 units of ethene, right, then your polymer will be, assuming it goes in a completely straight chain, which it doesn't always, but your polymer will be 100,000 units long. Okay, that's what n represents, the number of units there are. Okay, there are all sorts of complications here, but again, even at A level, we don't go that much further with addition polymerization than we do at GCSE. The complications, just to sort of fill you in, might include the fact that there might be branches, so it might not be a completely straight line, and the idea that eventually you have to finish this structure with something, and they add special chemicals, you know, to basically cap off the structure and make it end, because otherwise, you know, it couldn't end with another molecule of ethene, right, on its own, because basically there would always be a carbon missing a bond at the end if that was the case. Again, that stuff, you know, is really for if you study polymer chemistry at a higher level, you worry about it then. Okay. Now, a bit of a technicality, right, is that we have to be able to name addition polymers. It's not terribly difficult. You basically just take the name of the monomer, put it in brackets, and put the word poly in front of it. Okay, so ethene becomes polyethene in the presence of the correct catalyst, and if you raise the temperature and probably mess about with the pressure as well. Like I said, you don't tend to worry about the specific conditions for these reactions. One final thing to point out about this is if you look up polyethene on the internet, you'll find all sorts of stuff about ethylene, polyethylene. That's what most people call ethene, is ethylene. But if we're sticking with the UPAC, you know, nomenclature, we should call it ethene. So then, we've just drawn a polymer diagram. Something else that we might be asked to draw is called a repeating unit. And this is a very closely related image. Okay, there are two sort of key differences. So the repeating unit for polyethene is just that, which is obviously an unfinished structure, right? It doesn't have the brackets and it doesn't have the little n, okay? So from a sort of nitpicky point of view, up here is a polymer diagram, down here is the repeating unit, right? Annoyingly, if you Google repeating unit, then you'll see it drawn with brackets, right? And you'll see it drawn with an n and stuff like that. To be honest, there isn't a massive difference between the two. As you can see, they're very, very closely related, but you know, it's kind of a technical distinction, right? Examiners will usually, if you're asked to draw a repeating unit and if you put brackets and an n, right, like the polymer diagram, they'd usually have a phrase ignore in that case, okay? But if we're doing it properly, there's your polymer diagram, there's your repeating unit, okay? Right then. Next job is to try and do a little bit of practice, okay? I know we're going from kind of zero to hero here because you've only done one example, but it's not actually as complicated as it seemed. If you're struggling to get going, then feel free to look at the first solution. But what you should do is at least pause the video and have a go, right? For each of them, you need to draw the monomer, draw the polymer, name the polymer, and then draw the repeating unit. So it's the same thing we just did, but with different starting materials. Have a go, pause the video, see how you get on. Okay, so, right, the first one to discuss is propene, okay? So here's our monomer. And we might as well discuss this, right? See how I've drawn it, right? I know that because I am trying to address a polymer issue, because that's what I'm trying to do is polymer diagrams, there's a particular way in which you should probably draw these things. Notice how I put the methyl group pointing upwards. So just to explain what I mean, if I just said to you, draw propene, what you'd probably do, understandably, is something like this, or the displayed formula, or whatever, right? That's propene as well. But by taking this methyl group and making sure it's pointing upwards, I've made it easier to draw the polymer diagram, okay? And the reason for that is, remember that the most important location in an alkene when it reacts is these two carbons, right? In the polymerization, it's those two carbons that are going to be forming the bonds outwards. Everything else is going to stay exactly how it is, and you can keep it exactly where it is as well. So that's good practice when you're trying to draw polymer diagrams, is locate the double bond and draw those two carbons horizontally, then put everything else vertically, right? And if you have to draw the molecule like I've just done here first to get your head around that, that's absolutely fine. Okay, but that's how all of these will be done. So there's your polypropene, there's your repeating unit down below. Obviously, if you had a go at this, and if you've got it like this or something like that to begin with, absolutely fine, because that's still propene. You would still be making polypropene, right? It doesn't really matter where you put the methyl group. It'd still be correct. All right, next one. So our monomer here, chloroethene, is ethene with a single chlorine atom attached, right? You then do the same thing again, open up the double bond left and right, put brackets and an N, and then with the repeating unit, you show that structure without the brackets and without the N. I think that one's relatively straightforward. Probably a bit easier than propene, to be honest. Next. So this one's a slight twist again, right? You might have realized by now that the same kind of logic applies with this alkene. So even though this is butene, I've not done four carbons in a horizontal line. I've focused on the double bond and I've put the other two carbons pointing upwards. Remember, they don't have to be upwards. They could be downwards. They could be on the left-hand side. It doesn't make any difference, right? But the important thing is that by doing that, as usual, I recognize that the double bond is where the reaction's taking place, and I make it easier for myself to draw the trailing bonds that then get the brackets put through them. This would be called polybutanene, right? Because the isomer of butene that it is to begin with is butanene. So monomer is butanene, polymer is polybutanene. And there's your repeating unit. Okay. Last one. Similar sort of story. Tetra means 4, fluoroethene. Okay, and polytetrafluoroethene. There we go. I don't think there's loads that needs to be discussed there. Some of these polymers that I've shown you, or asked you to draw, I should say, have, you know, different names, right? And are known for certain uses. I'm not going to worry too much about that for now. PTFE has some kind of, you know, non-stick properties, so it appears in you know, saucepans and stuff as a coating. That's the one we've just done. Polytetrafluoroethene, abbreviated PTFE. You know, there are lots of things that we could look at in terms of uses, but we're not going to look at that right now. I just wanted to focus on drawing the diagrams. Right then, so that's pretty much the main part of the lesson done. I am going to do a little bit about something slightly more complicated, but it's not going to last very long. So you can either tune out now, or if you want to, again, kind of expand your knowledge a little bit, then you can stay on the video. So something else that's probably worth mentioning is there's a class of addition polymers called copolymers, right? So everything we've looked at so far has what we call like an A, and so on structure, basically meaning it's the same monomer over and over and over again, right? And that's what you get if you just heat, for example, molecules of propene, right, on their own in the presence of the right catalyst. But you can also get things with kind of an A, B type structure, and you can sometimes do this by basically mixing different types of alkenes, and we call this kind of polymer a copolymer because it's made up of different units, not just the same one over and over again. So the idea is, let's say we take chloroethene and propene, right, and heat them in the presence of an appropriate catalyst, then what we might get is a polymer which has this repeating unit. So what we're doing is we're making the repeating unit, 4 carbons long instead of 2 carbons long. Now, I'm simplifying massively because it's actually a bit of a random process, and I've said it might go A, B, A, B, A, B, but actually it might go A, B, B, A, B, A, B, 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 A. So it might be completely random which units you get, right? You're going to get a mixture. But the idea is that there are these things called copolymers, and these do appear occasionally in more challenging A-level polymer questions, right? Things like this, but they are very much the exception, not the norm, right? So that was just a little word about copolymers. I'm going to leave it there, right? I'm not going to do loads of stuff on addition polymerization. It'll be something that we revisit time and time again later on. All right.